Warner from University of Maryland Observatory. I don't know if you're director or chief bottle washer.
They call me coordinator.
Coordinator of the University of Maryland Observatory. She does a lot of outreach. She's worked with Novak many times in the past and invites us to help her and to be helped by her at the observatory. She's going to talk this afternoon on ADVS, which is a system that the University of Maryland is developing for occultation measurements. Elizabeth, thank you for coming.
All right, well, thank you for having me, because this kind of made sure that I got out here to almost heaven again. It's been almost well over 6 years since my husband and I came last time. So I'm going to talk about the Astronomical Digital Video System, ADVS. It is a beta system that we're testing out right now. Now, why are we doing this? When I was in college, I had to do a senior project, which you can pass around. This was, my professor basically said, you're going to do occultations. You're going to do grazing occultations. Now, first off, who knows what an occultation is before I get too far? Who does not know what an occultation is? All right, so we're good. How about grazing occultations? We're good on grazing? Anyone unknown? Don't know? Okay, so grazing occultations, basically when you have the moon moving through the sky, occasionally it passes in front of a star, and it occults the star. But if you're sort of on the edge of the shadow of the moon, then you're going to see the star seeming to pass along the edge of the moon. And since the moon does not have a perfectly smooth surface, it's got mountains and stuff that we're seeing in profile, you'll see the star pass behind the mountains and reappear in the little valleys. And so you can kind of get a profile marking for the moon. So they have observers who are lined up along, perpendicular to the shadow path so that people can observe it. Someone will end up observing a full occultation. Someone will be far enough out that they'll see a complete miss, and then some people will see different amounts of occultation along the edges of the moon. So he assigned this to me and another student. We did a senior project out of it. They published it kind of like a thesis, and it was really interesting, actually. And so I've tried to continue doing some occultation observations over the years, and we occasionally get requests for it. In addition, it's a fairly easy project to do for students because it's not overly time sensitive, or doesn't take up a huge amount of time to do an observation. To observe variable stars or binary stars, you often have to observe for many hours, and you want over many nights, and you want to sort of fold the data to kind of get the light curve out of it. And with an occultation, it's going to be much shorter duration. In fact, most of the time is spent on the setup and the takedown afterwards rather than on the occultation itself. So we kind of wanted to set up a system for students. When I did the occultations, the grazing occultations, we basically had a tape recorder, a time cube, and we just sort of visually made the observations. Sort of saying in, out, as the star disappeared behind the moon, mountains of the moon. And so that has the personal reaction time, how quickly a person can react to what they're seeing and everything. And so there's a little bit of difference with the times there. So we kind of wanted to make sure that the system we set up was a little bit more foolproof, because students weren't going to be doing this a lot. It would be different students each time. And so we wanted it to be fairly easy to learn, and yet at the same time somewhat foolproof because it is being used by students. As part of the fees that the university collects, they collect what they call tech fees, student tech fees, for their science labs so that they can do upgrades to equipments and such. And so in 2013, we kind of had a wish list of items, and we put together that wish list, and one of the items we decided to do was to get a video camera to do occultations, and in this case we're focusing mainly on asteroid occultations. Okay, so we're using student tech fees. We started doing research on what systems were available at the time and what we wanted to maybe go with. A lot of the International Occultation Timing Association members who do the asteroid occultations are using analog video cameras, and they have video time inserters that kind of insert them into the analog videos, but there's a lot to it apparently, and so they seemed a lot harder than I felt it needed to be. So we found out about the ADVS system. It's being put together by some observers in Australia who are occultation observers, and they're trying to put together basically a digital video system with the GPS time inserter. And basically it has 3 components to it. It's got a Point Grey camera. Point Grey is one of the companies that makes cameras, and they make these itty-bitty tiny little cameras, which are really cute. And they fit into the eyepiece basic holder for the most part. There is a component that they build, they call it the HTCC. Basically, that is the GPS receiver. And then you have your computer controlling it all with the software and stuff. So sort of the 3 components to it. We are beta testing the system, so they haven't really finalized some aspects of it. We're actually going the MacBook Pro with a Linux OS on it. Some of the other guys who are testing it are using WinPCs with Linux on them, so there's some differences there. And whenever we have issues, there's really only one other guy doing the MacBook Pro version, and so getting feedback and trying to figure out what's wrong sometimes is interesting. Okay, so we put this order in July or in 2013, and we ended up receiving the equipment through late 2013 and early 2014. But by the summer of last year, we still really hadn't gotten very far, because we were having issues, a couple of different issues. I only work part-time for the observatory, and my technical advisor is even less time than I am. I am not a computer guru. I'm certainly not a Linux type or a Mac type, so there was a lot of stuff going on that was confusing. Getting the Linux to control the MacBook Pro properly so that it doesn't overheat was a big issue, and so we ended up, how familiar are you with Linux and doing Linux stuff? There's a lot of upgrading of Linux and then downgrading until you figure out what works with your different things of software. It's a pain in the butt. Yes?
Why was the laptop overheating? It seems kind of strange.
Because the Linux OS wasn't properly controlling.
Oh, the temperature of it?
Yeah.
Oh, I see, okay.
So, basically you've got MacBook Pro, but then you've got the Linux OS on top of it that's supposed to be controlling everything. And since the Linux is not native to it, it doesn't always play nice. And so, yeah. So figuring out at the same time the software for controlling not just the camera, but for this whole package kind of only worked with certain versions of Linux. So if we upgraded too far, then the other software wouldn't work. So we were figuring it all out, and we really didn't have it working yet as of July of last year. And then in the fall, we got really lucky because we had a student who was looking for an internship, and he was more of a computer geek, and he was familiar with Linux, and so we put him to work, and that was his task, get this working. And he got it working so that by mid-late fall of last year, he actually got working quicker than we anticipated with all the issues that we'd been having. And so we were actively doing tests with it, so that in the fall and over the spring, I actually had other students who I was training to actually use the system to do some occultations. Now, some of our first observations and tests were just done with an Orion short tube set up on a tripod, and I was trying to do that mainly to get a nice, fairly big field of view. And you'll kind of see a little bit later on that when you attach it to other cameras, the field of view is significantly smaller. And so we wanted a nice big field of view so we could have enough stars so we could figure out what we're looking at. And I was thinking that this would maybe be a good portable setup. So I actually carried it out to Colorado last winter. You don't even realize I did that, did you? That's the nice thing about small and portable. So I was able to hide that in my luggage, and he didn't even know I was doing it. and to do a sort of portable setup. The biggest problem was it's not steady enough and there's no tracking. So even if I found my target star, which we often did, we'd have to keep adjusting to make sure it didn't track out of view during the occultation itself. In January, basically, we had a really good opportunity for a really good occultation event, and we made our first observation. Fortunately, it was winter break, so my students weren't around, so we ended up doing this ourselves. And it was asteroid 489, Comacina, occulted some really faint star at pretty early in the evening, roughly 7:40 in the evening. So it's nice and early, it wasn't midnight.
What are we looking at?
So what we're looking at here, do we have a laser pointer? No? Maybe? And you know what? I have 2 of them in my backpack back in the car. This is a field of view printout from Starry Night Pro that shows the field of view of my 6-inch refractor with a CCD camera, ST10 camera. And the target star is this little faint guy right there. Okay? And you'll see some other charts a little bit later on where I actually have the overlay for the ADVS as well. I didn't have it yet for this first one. But we basically, once we set it up on the 6-inch refractor, I have the CCD camera permanently attached to the telescope, and I have a little slider in between so I can switch from visual observing to the camera fairly easily. Okay, and so this then sits into the eyepiece instead, so I can take CCD images, do the little slider, it's just a flat mirror, kind of like a flip mirror, but it slides in and out instead, and then the ADVS sees things. But that was sort of my finder chart.
It's a small pointer, front button.
Okay, front button. So yeah, it's just a very, kind of field of view, and I print these using Starry Night Pro, have it set up for my different cameras and telescopes that we have. So this is then a CCD image of that field of view. And so the bright star, little star, and that was our target. This, no flat fielding, no darks. This is raw. We're just quickly trying to make sure that we're looking at the right field of view. We're not trying to get a pretty picture. We just want to make sure we're looking at the right stars. Now, I've since processed the image through using astrometry.net so that it could identify some stars and sort of do a world coordinate system overlay to it. You kind of have the little, I'm pretty sure north is up and east is left, but I could be wrong on that. But basically, if we kind of flip back and forth between the 2 images, they match up really well. So you got the bright guy here with the little faint one. You got these 2 guys. You have sort of this triangle down here. So you got the bright guy up here with the little guy, the 2 stars here, the triangle. So everything matches up nicely, which is always good. So then the observation, we collected the video. Basically, it generates a video, and we can select what frame rates that we use. At this time, we were using 3.75 frames per second, which actually detected that faint star just barely. We have those other bright stars that we can use as guiding or comparison stars. And then we run it through another program called Tangra 3 that then sort of processes it using differential photometry. And again, we're not overly concerned about what the values are, the counts or anything, or magnitudes here. What we're looking for is that little dip right there. Okay? And here, if we kind of zoom in on that section, you can kind of see there's a very nice little dip. And we basically measure how many seconds or fractions of a second that is. We then submit a report with our coordinates where we're observing. And that's really nice because you get those coordinates from the you've got a GPS receiver here, so it tells you everything. And we submit our report. They combine it with a whole bunch of other observers. And when you combine it, you kind of can then see the shape of the asteroid that occulted the star, because you're seeing it basically in silhouette. So one person was observing, and they saw a miss. They didn't see anything. But this is always good. So when you look at the predictions, and I'll show you a little bit later, you always kind of sometimes want to be outside of the shadow as well, so you can kind of be a limit sometimes on some of the observations. This person saw it disappear for a very short time, longer time, this amount, so you kind of then do a best fit to it, and you kind of get the shape of the asteroid. And you can actually go through sort of where the results are, and there's a page of results for all of the asteroid occultations thus far, and you can also look up past ones. And if you look through some of those, you'll sometimes see that there's like a whole slew of observers who all saw misses. And what it is that the asteroid path has shifted in its orbit, and so where they were expecting to see the shadow, where they were expecting to see an occultation, didn't actually happen, and it shifted. And so a lot of people saw misses. Meanwhile, on the other side, where people were expecting to see misses, they saw occultations. Okay? And you can sometimes get some really interesting shapes for the asteroids. Sometimes they're very elongated. And you have to remember, this is sort of a projection, so we have no idea. It could be very long. We may be seeing the short end. We have no idea. So we're just sort of seeing part of it just sort of flattened there. Just for reference, our observation ended up being right about here, almost midway. This purple observer here actually ended up lining up with where they thought the center of the shadow path was going to be. So you can kind of see that if the original expected shadow was going to be centered roughly here, you can see how it's shifted down a little ways.
Well, do you think it's the asteroid that shifted, or that they got the computations wrong? In my opinion, they got the computations wrong.
No, basically they don't know the positions of the asteroids well enough, and so yes, they shift. I mean, they're not the exact same orbit every time. They do shift over time from various Yarkovsky effect and that effect. So it does shift.
Were these all people using the same setup?
No, different setups.
Different kinds of equipment?
Different kinds of equipment. There may have been a visual observer in there. There may have been, a lot of them are probably using other kinds of video cameras. But they pretty much, out of the folks here, I'm probably the least experienced out of the observers, to be honest with you.
And 3 might have had a timeout, right?
So, what do you mean?
Looks like his gap is about right, but it's just shifted. Is that right? From in the middle to down and to the right.
No.
No, the one that's marked subscript 3.
All right, well, no, subscript 3, so it's hard to read here inside, but so 3 is actually a series of dots. Is actually a series of dots that it was normally, sometimes you have an observer sitting there and sometimes you don't. And so they overlay kind of where in the projected sky the center line would be, and then from there they do so it turns out that so 3 and 4 are sort of the same line, because 4 is an observer sitting at what was the predicted center line. So they observed something, but they turned out not to be on the center line. I was closer to the center line. Okay, so we had a really successful observation. We even sent in our video, since that was our very first time, I even provided my video and all the files to some other more experienced observers so that they could derive and do the processing and make sure that I figured it out. Then the spring came, and as many of you know, we had a really nice and cold spring this year. And at that point, it didn't matter how much the laptop was overheating because it was really happy in the really cold winter. The problem was that with the students, they weren't always very careful how they were putting away the cables, and of course, the cables would get really, really stiff in the cold, and so one of them broke, and we didn't really know it broke. We just know that things didn't quite work after a certain point. So we eventually managed to, in late March, early April, diagnose the problem, figured out we had a bad cable, so we replaced it. We had an ongoing issue all since the fall about not being able to change frame rates. We were kind of stuck on 3.75 frames per second, and it was supposed to be able to change, up to 30 frames per second to a couple seconds per exposure, and we didn't have that. And so they told us, you need to send us your INI file, you need to send us this, and it turned out to be a fairly simple fix, which we did, and then everything worked hunky-dory. Wrong way. So since then, we've done a number of attempts. So in late March, we tried to do 2 of them. We really didn't get either one. The building got in the way of the first one, and the trees got in the way of the second one. They were on the same night. And so not only were the building and trees in our way, but then we were still having the equipment problems. We still had the broken cable. Then we had this one end of April. This was after we managed to get everything fixed. And we call it a successful miss. So we didn't observe an occultation because we were outside of the shadow path, but we did observe the star successfully, and we were observing at the correct time and everything, so we observed a miss, successful miss. The next one we tried was a cloudy night. Then this one we were pretty excited about. There's a whole bunch of people signed up to try to observe this one. You've got a nice big asteroid and everything. And nothing happened. And then we started looking back into, the IOTA user group archives, and it turns out that back in April or so, they made a notice that, oh yeah, if you look up this event, it's actually a non-event, and it's a mistake in the software, and but of course, yeah. So anyway, so non-event. Then more recently, we tried to observe this one, Jovita. Again, there were several people signed up to observe it. I had some students trained to do the observations, and it was a cloudy night. And then over the week, so this is just last weekend, we had this guy, Mike Penston, asteroid Mike Penston, and again, I had these 2 students who were volunteers actually, because we're in our summer break. One's a visiting grad student, and the other one's an undergrad who's just really interested in astronomy. So I trained them up before I went on some vacation, and they did the observations. So here we have another starry night output. The bigger box is the field of view of the 6-inch with the CCD camera, and the ADVS is the field of view here. And the target star is the bright guy right here, so it's kind of a bright star. Now you notice that I don't have it dead center in the frame. When I was producing the charts for the students before I left, I kind of shifted it to try to hint to them that when they were centering up the target star, that they should also shift it a little bit so they could get these other bright stars in for comparison, so we could have comparison stars. Because you notice that there's not that many stars in the frame, not many bright stars at all, and so it would have helped. So again, the CCD field of view, target stars, some faint stars, but in terms of what, and they have it pretty much dead center. They didn't shift it, and so some of these faint stars in the actual video don't show up very well. This guy is outside of the frame. These guys are outside the frame, so we kind of lose some of those. Now this is a CCD field of view, so the bigger field of view. It's probably like a 30-second exposure, maybe a 45-second exposure. I don't remember what the students used. And I'll play the video later just because I don't want to switch computers right now. Okay? So what is our procedure? So we use a program called CultWatcher, which basically lists upcoming occultations for your location. You basically input your latitude, longitude. You can actually input several different sites. So I have it set up for the observatory. I have it set up for our observing deck in Alexandria. I have it set up for my stepdaughter's house in Colorado. I have it set up for several other places where I'm likely to be observing, and then I kind of scan through and see what's coming up. And you have a main list of asteroid occultations, and then you can select some to follow, and they sort of show up in this upper list up here. And let's see if I can do this. where did my, there it is. So even though it's not connected to the internet, we can sort of show you kind of how it looks. So for Jovita, oh, no, it's not, it didn't switch, did it? Didn't switch. Okay, fine. So I can sort of show this to y'all, but I've got the software sort of set up here as well. Fine. So you can click on a particular event. It will then sort of show you your position relative to the shadow path. The region in orange is sort of the 1 sigma, sort of the region that the asteroid can shift in terms of where they expect it to be. Then there's some little markers that sort of do a 2 sigma and 3 sigma boundaries. The size of the shadow depends on what asteroid it is, how far away it is from us, how big the asteroid is. So sometimes it's a very tiny shadow path, and sometimes it's a very nice wide shadow path. And then the other little tick marks are basically other people who've announced that they're going to observe that event. And the idea is to try to get as many people observing the events as possible. So you can go through that. You've got information about how bright the star is. You've got information about what the potential drop in magnitude, if you're sitting at the center of the occultation, how long it lasts. So a bunch of different information. If you click on some of the options down here, you can sort of see an online Google map that sort of shows the location of different observers. Now, even though this sort of makes it seem like we're all in a line, we're not. Okay, the idea is a shadow path is sort of just like lunar or solar eclipses where the moon's shadow goes across the Earth. You can actually have people in different parts of the country, and so long as they don't have to be perpendicular to, relative to each other, they just have to be perpendicular to the overall path. Okay, so you can get people all over the country observing it. Okay. So right now I've kind of highlighted this one called Sicily, which is coming up next Thursday on the 20th. So I'm going to have my students trying to observe that one. It's not a very high-ranking one, so they don't expect a lot of people to observe it, mainly because it's such a narrow shadow path. And it's just under a second duration if you do see the occultation. But it's got a good magnitude drop, so we'll try for it anyway. Maybe we'll get lucky and it will pass over us. Okay, so kind of zooming in a little bit. This is the predicted time of the event. They're estimating a plus minus 42 seconds for it. So we have to start observing early enough that we don't accidentally miss it. Once it happens, if you're in the shadow, it probably would disappear no more than a second. The star itself is magnitude 9.3, and with the asteroid going in front of it, faint asteroid, expected magnitude drop is about 10.8.
So it's going to go to 10.8, or it's going to go down to 20.1?
Roughly 20.1, yeah. Because the asteroid magnitude, it's not in this, asteroid magnitude is 20.1. Yeah. Now sometimes when you start to get asteroids that are almost the same magnitude as the stars, the calculation of that expected magnitude drop starts to not be quite as mathematically simple. Because if you have a 9.3 asteroid trying to occult a 9.3 star, you're really not going to see. You have the combined light, which is slightly greater with the two of them, so the overall drop just goes back to 9.3, right? Yeah, yeah. Okay.
You got one 9.3 source instead of two.
Well, no, but as they're coming together and as you're measuring them, until one occults the other, you're basically, you can't resolve them as separate points. You're still just measuring them as one single blob. So then the total amount is slightly more than, or slightly brighter than 9.3 at that point.
So as they get together, you should see a slight increase and then come back to normal and then an increase
Yeah.
again.
But the idea is, how far in advance do you need to start observing that?
Right.
Okay, I mean, if you're taking lots of frames and you start too soon, I mean, you're getting gigabyte for a 3-minute video. You're getting a gig of video, so it adds up quick. All right, so here, here's the chart that I'm going to print for my students for this one coming up. The target is this bright star right here. We've got plenty of nice comparison stars and such, so they should have an easy time doing the data processing for this one. So I use Starry Night Pro to generate my finder charts. We also kind of determine maybe which star to do our initial telescope alignment on, so that we're kind of, because we input the coordinates, so you have to make sure your initial alignment is good. So we'll probably use either Nunki or Dobby over here in Capricorn, one of those two, to kind of synchronize the telescope and then move to the coordinates of that star. And on the night of, basically the students go through with the telescope setup, but at the same time, one of them's also working on getting the ADVS system up and running, because it has to detect the GPS signal and get all of its connections. And it is a beta test system, so sometimes it doesn't really start up right, and you have to start it 2 or 3 times before it actually makes its connection and stuff. You can adjust the gamma and gain for the video, the frame rates, to kind of make sure you can see the stars, that you see some comparisons and everything. And then to make sure that they start recording far enough in advance that, so this one has plus minus 42 seconds. So we should probably start videoing a good 2 minutes before the actual event and keep going for a good 2 minutes after the event. So right there, you've already got 4 minutes for sure, and more than likely we'll end up with 6 minutes of video. Okay.
How long does an average occultation last?
So they can last anywhere from a couple of seconds, several seconds, tens of seconds, to fractions of a second. And and that's where video becomes very important, because it's still on the order of seconds. Even if it's a 5-second occultation with standard CCD camera, it takes, even if you do a 1-second exposure, 1 second, it still takes almost 10 seconds for it to download, right? So you would basically get the one and then miss it. And if you said a 5-second exposure, you don't really know exactly, or 6 seconds, and it was a 5-second event, you don't know when it started exactly. So with the video frames video several frames per second, you can delineate that a lot better. Yes?
So with the video camera, are the frames being looked at individually, or is there software analyzing the video feed?
So we have a software called Tangra 3 that's also put together by these guys, and the Tangra, this one's also used by the analog video users as well, to get their analysis out of it. And that's what some of those earlier light curves were outputs. That's the output from the Tangra 3. So we basically import the video, we tell it which one is the target star, we identify other stars to be comparison stars or guide stars. We can tell the system if there was strong flickering, whether it drifted through the frame or we were tracking. And it will actually even when it was, when I did my initial tests on the short tube, so that the target star was drifting through my frame, it actually followed it pretty well. So it did really well on that. I had a much harder time analyzing the most recent observations with Mike Penston, mainly because there's just really no bright stars. I mean, the target itself was visible, but it was the brightest thing in the frame, in the video. And so trying to find some comparison or guide stars was a bit difficult. Okay, so then afterwards, after you process the video through Tangra 3 and get your numbers, Well, first off, you'll usually can report what, if it was cloudy, kind of submit a report. We couldn't observe it because it was cloudy. Okay, fine. If you had a miss, you can report that as well. We did observe the right star, the right time, but it was a miss, and you report that. But if you had an observation, you can actually, they have a form, an Excel spreadsheet that kind of gets auto-generated with some information that you provide to it, and then you just sort of fill in some of the other information about the times and any notes or whatnot into it. And I'm still learning this, so I haven't figured out exactly how to tell them what my signal-to-noise ratio is for the system. It's something I'm still learning. But we submit this, and then they'll combine it with any other observations. Right now, because it's such a short, this one had a predicted occultation of only 0.7 of a second, and I'm reporting a half-second occultation. That's so fast. It's basically only 3 frames, okay? That is so short they kind of want someone to double check me, which is fine. So I'm going to provide them the video, and they'll process it as well. All right, so the resources, and so we've got the program, CultWatcher, basically does the predictions. It comes out of a database that some other guys generate, and it's a little bit easier to use. There's another program called Occult, which is a little bit more hands-on, where you can go in and you can say, I have an asteroid, Asteroid Ahern, he's my boss. When will that asteroid be occulting some star? And so I can go through and sort of search for that particular one. I have it on my computer at work. I haven't quite gotten that one to work right. So I use CultWatcher. I have it running on all of I have it on this one, I have it on home, I have it on different computers. It works really well. There is a user group, the IOTA user group, for getting a lot of help. They're pretty active. Then you have your IOTA website, your main IOTA website. This one is for their meeting last year, and there's a couple, they actually have the slides as part of a video that's on YouTube, so you can go and look at some of the presentations that talk about more of the basics of occultations and give some other background. So you can kind of go through the different presentations, figure out, hey, I want to see this one. So all of those videos are actually available, freely available online, and that's the link to them. And then you have, like I said, Occult's a little bit tougher to use. So those are my slides. But what I've done is I've brought the setup, and so I've got this running. And like I said, it's a very small camera. When we first got it, we were kind of pretty amazed at how small it was. At first, we were thinking that we would have to switch it out with our CCD camera. And I was thinking, I really don't want to switch CCD camera with another camera, because that's just a pain to do. So I actually went and bought some additional weights, because I knew this was pretty light. I was like, we're going to need some extra weights, because this one's much lighter than the CCD camera. And then we got it, and we were like, yeah, we're not switching. We're just going to put it in place of the eyepiece. And so basically, it fits right into the eyepiece here. And so, whatever system you have is basically a 1 1/4 fits in, and then you focus it. We have a small focus differential between what the CCD focus is and what this camera has on my 6-inch telescope, and so we have that marked so we can flip back and forth between them. And then this is the video, so we've actually got it already connected and initialized. You can sort of see the counts. That's the time signal right there, and the time jumps are based on what frames per second I'm using right now, so it's sort of at the default of 3.75, but I can change the frame rate. Oh, no, you're not. Oh, wait a minute. Frames per second. Frames per second. So then I can...
So you can change that number now, right?
Yeah, I can change it now.
Right.
So that's what I'm sort of showing you. So I just changed it, slightly longer exposure, so fewer frames per second, 1.88. I can go the other way. Oh, that's slower. I can do 7.5 frames per second. You sort of see the numbers are going by much faster there. Wrong way. 15 up to 30 frames per second. And then you can go as slow as 4 seconds per frame. So 4 second, 5 second, what is the longest? 8 seconds per frame. Okay, now that might make it easier to see any stars in the view, but if you only have a 7/10 occultation, then you don't want this long of an exposure. Yes?
It's the exposure, it's not the time. Well, I guess it's the time between
It's the
exposures
same thing.
also.
Right, so the camera is continuously capturing light,
Right.
and the longer exposure time you have, then the less frames you get.
Right.
Because, you're taking the same amount of light, just
So
putting it
it
in
uses
boxes.
the entire exposure time.
So
Pretty much.
3.75 frames per second is roughly 0.3 of a second per frame. Okay? You can also adjust the gamma and the gain on this, which are, when I was explaining it to my students, were brightness and contrast for it, very simply. Right now it's not changing much because I have the cover on the front of the telescope, but in theory, if we were to aim it somewhere that could actually see anything. All right, let's not do 8 frames per second. Still very bright. Let's see if we can get something.
Do you want one of us to oppose it? Somebody else?
I'm just trying to get it so it's not overexposing too much. Because right now it's basically just overexposing. It's so bright in here, it's really sensitive. And we managed to get it to work, sort of in daylight, but looking at some really distant trees near sunset. So the sun was going down and things like that. But it's still really bright in here and everything. You'd be surprised. Oh, it's not going to be there so y'all can see it. Yeah. So you would be able to get that. Now,
Point gray grasshopper.
yes, yes. So before coming out, I went online. I went and looked at a CultWatcher to see if there was any occultation events for this weekend, input the coordinates for TMI. Nothing this weekend, nothing. So beyond looking at maybe some practice, just other stars later on, which we'll probably do tonight, there's no actual occultation events this weekend, unfortunately, to play with. But we'll point it at some stars, kind of show what the stars look like on here, and kind of do our hands in front of it to pretend do an occultation. And I'll be happy to show the CultWatcher sort of on here. It doesn't have internet connection right now, so not all the information will be accessible, the online Google map and things like that, but we can sort of still show you up close what some of the stuff looks like. And that is it.
Can you run it like this, where it's not saving it?
Yes.
Start capturing.
Oh, yes. So, yeah, right now it's just running, and then when I'm ready to record, then the magic button is record. Assuming I've got it. Yep, there it's recording now. So it's recording, and then stop, magic stop, and then it stops. And it automatically, we have it already set up for the folder it saves into, and we have it. So I can actually pull up, so I'm going to, let's see here, how do I want to do this? I'm actually going to close this guy, escape. And I'm going to pull up Tangra and show you the video from the Comacina. But you'll probably want to...
Can we flip the monitors and put it on the screen?
Jerry, can you bring the HTC and just put it on the chair? Assuming I...
Yes, the upper left-hand corner of your screen
right, so file, open a video. So this is the most recent one, this Mike Penston one. And
You may have it in shared monitor mode.
and I don't know how to do it in Linux.
Up in the lower left corner, that red one has 4 quadrants on it. It's not sure how to enable.
Could just grab the corner and drag it.
Hey, did it?
Right and drop.
There we go. Now I can't see what I'm doing. All right. And now I can't get my mouse either. Oh, why can't I get my mouse?
Move it to the left.
I know what it is. It's sort of a dual screen thing.
Can you mirror displays?
I see what it's doing. So it wants this one. I see what it's kind of doing, but, and I know how to fix it on a regular Mac, but because this has the Linux on it and I've never used it for sort of projection, I'm not